For 3 rotations, we're going to answer this essential question. You want to be able to rotate a figure in a coordinate plane, be able to explain that. Things that we're going to do, we're going to be performing rotations. We're going to be performing compositions involving rotations. We want to identify rotational symmetry. Core vocabulary will be rotation, center rotation, angle of rotation, rotational symmetry, and center of symmetry. Alright, core concept, rotation, and it is a transformation in which a figure is turned about a fixed point. That point is called the center of rotation. Rays drawn from the center of rotation to a point, and its image form the angle of rotation. Okay, so looking at this diagram right here, this right here is the point of, or the center of rotation. Right? So I have this little flag-shaped drawing here using RQ, and I'm taking it from here and I'm creating a 40-degree rotation. Okay, so I'm turning it from a fixed point, P, and it's kind of tilted this direction. When I rotate it, it turns a little more vertical. Okay, so we call this the angle of rotation. All right, rotation about point P through an angle of x degrees map every point Q in the plane to point Q prime, so that one of the following properties is true. Okay, so you'll need to know these properties. If Q is not at the center of rotation P, then the distance from QP is equal to the distance from Q prime to P prime, and the measure of angle QP Q prime is equal to x degrees. Or, if Q is the center of rotation P, then Q is equal to Q prime. Okay, so that's basically saying that I can rotate it from a point that's not on the shape. Okay, or I can take the shape, I can take Q here and I can just rotate it about that point Q. Alright, and then important thing to know, this direction that we're going this way towards the left, that's counterclockwise. Right, going towards the right, this direction is going to be clockwise. Okay, and we typically use counterclockwise. That's kind of the standard. If it is something other than counterclockwise, the directions will tell you what to do. Alright, so here's example 1, and I'm kind of explain the core concept here with an example. So here's this point P. We want to rotate it 120 degrees. Notice it doesn't say which direction, so kind of the default is counterclockwise. Alright, about this point P. So the way this works is we have the distance, or we draw a ray or segment from P to A. Right, and what we're going to do is we're going to make an angle from point P, and because it says it's 120 degrees, we're going to line up our segment, and I want to measure out from here 120 degrees, which would be here. Okay, so if I draw this and I connect it, that's going to create me a 120 degree angle. Now the important thing to notice is that the distance from A to P has to equal the distance from A prime to P. So this distance has to be the same as this distance going in the other direction. So I'm going to estimate this to about 2. So from here to here, okay, this point right here is going to be A prime, because this segment would be congruent to this segment. And then I do the same thing with B and C. Alright, so what I did is I went ahead and repeated the process from P to B, and then I copied that distance to B prime. Did the same thing with C. So this segment from P to C is the same distance as P to C prime. So copying all of these, making that 120 degree angle for each one of these, creates this new triangle here. And it's rotated 120 degrees counterclockwise. Right, and then this next picture, this next little information says that you can rotate something more than 180 degrees. What happens is you take this point A and you rotate it 130 degrees, 220 degrees, 310. Once you go back 360, that's going to take you right back to where you were if you go all the way around. All right. The important thing to know about that is that when you rotate these things, there's a pattern, kind of like when you were reflecting across the X and Y axis and across the Y equals X line. There's some things that happen. So if you have a rotation, a 90-degree rotation, what happens is you flip the B and the A, and you take the opposite of B. Okay, 180 is here. The X and Y, the A and the B stay the same as far as the position, but we want to do the opposite. We'd have a negative A, negative B. Okay, and then here's the rule for 270. Alright, so here's example 2, and we're going to look at using these patterns. The first one, for example 2 that we're going to look at is 270 degrees. Now that when we have a coordinate AB, okay, what happens to that is that we got B minus A. So for our coordinates, R is at 3, 1. So we go to R prime, our new coordinates. That's going to be, I'm flipping them, and then I'm changing the sign on the second one. So it's going to be 1, negative 3. All right, S is at 5, negative 3. So when I map it to S prime, I'm going to flip them. Okay, and I want the opposite of the X value here, so it's going to be a negative 5. Oops, I looked at that wrong. T is at 5, 1. So this is going to be 1, negative 5. T is at 5, negative 3. So T prime is going to be negative 3, negative 5. U is going to get mapped to 2, or it is 2, negative 1. We're going to map that to negative 1, negative 2. Alright, so we're going to graph these. Okay, when we graphed it on the coordinate plane, this is what we get. Alright, and as we talked about with the other transformations, the translation and reflection, a rotation is also considered what's called a rigid motion. Okay, now we got an example number 3, which is going to be a composition. We're going to look at the reflection and then a rotation. So we're going to first reflect this segment RS on the y-axis. So doing that, I'm going to get R prime. It's going to go from the y-axis. That means it's going to go equidistant, if you remembered. So R prime is going to be there. S prime is going to be here. Alright, so there's my reflection, and now I want to rotate it 90 degrees about the origin. Okay, so that means I'm using my rules of rotations. I'm going 90 degrees about the origin. So that means I'm going to map my two coordinates. My AB is going to become negative BA. Okay, so I flip them and I change this, the opposite of the B. So R prime was negative 1, negative 3. I flipped them and I want the opposite of the B value. So here it was negative, it becomes positive, and my A value doesn't change, so it says negative 1. S prime is at negative 2, negative 6. When I rotate it, S double prime is going to be 6, negative 2. Okay, so let's graph those. That puts R prime here, double prime, and S double prime becomes 6, negative 2, which would be here. Alright, and so that would be my composition. We reflected it across the y-axis, and then we took it and we rotated it 90 degrees about the origin. All right, now we got some rotational symmetry. All right, and it's just looking at when the figure can be mapped onto itself by a rotation of 180 degrees or less about the center of the figure. This point is the center of symmetry. Okay? And we can look at it clockwise, counterclockwise, it doesn't really matter. In this case, I can take this octagon here and I can rotate it 45, 90, 135, 80 degrees, and it's always going to map onto itself. Alright, so for this shape, I can basically rotate it from the center, and I can take all these little vertices, and I can move this vertex here, and I could lay it on top of this vertex, and it would be the same figure. The same thing, I can go all the way around each one of these, and I would have the identical shape. They would map perfectly on top of each other. Alright, so this brings us to our next example, number 4, and we're looking at a parallelogram and a trapezoid, and we want to look to see if these figures have a rotational symmetry. Okay, so what I want to do is I want to create a point where I want to look at the center on both of these. All right, and if I were to rotate these with 180 degrees or less, would it map onto itself? All right, and then for this particular, for the parallelogram, the answer is yes. I could take this and I rotate it 180 degrees, and that would put it on top of itself. So I would be able to rotate it from here to here. I brought this over 180 degrees, it would map onto this vertex, would map onto this vertex. Same thing if I went in this direction using this vertex and I went 180 degrees, it would map to this one and it would fit perfectly. Right, if I do this using a trapezoid, if I mapped it this way, it's not going to map onto itself. I would just basically turn this and it would look something like that. And so it wouldn't map perfectly onto itself. So a parallelogram, yes, it does. Trapezoid, no, it does not. Okay, example number 5, we want to look at an equilateral triangle, and we want to identify the line of symmetry and rotational symmetry. Right, and because it is an equilateral, it's what's called a regular polygon, it is actually going to have 3 lines of symmetry, and each of them are going to go from one vertex to the opposite side, this direction. Okay, I can rotate it, and since it is a regular polygon, it's going to map onto itself. Now the question is, what's the smallest degree that I can rotate it so that it does map onto itself? Okay, and then I want to figure out the smallest angle that I can rotate this and where it will map onto itself. So if I go all the way around, that's 360 degrees, right, and I divide that by the number of lines of symmetry. Since there's 3 lines of symmetry, right, 360 divided by 3 gives me 120 degrees. So that would be the angle, the smallest angle that I would rotate it, 120 degrees, and this equilateral triangle would map onto itself. And a little something for you to think about, and so we can talk about in class. Can rotations of 90, 180, and 270, and even 360, can I take these rotations and write them as a composition of reflections?